All right, hello, I'm Sam Goldstein. I'm a grad student at Columbia, and today I'm going to be talking about reconstructing wiggly signatures of the cosmological collider. It's a recent paper done in collaboration with some people in this room, including Oliver and Will. And so this will be about the bispectrum, so the three-point function and momentum space, typically of the matter field. And the question is, why should we care about wiggly bispectra, right? Like, what am I saying? Why are we doing this? And I think there's actually good reason to study this. So starting from things that we know exist, the baryon acoustic oscillation imprints oscillatory features in the bispectrum. There's actually been some detailed work studying this. Going a little more speculative, you can have these sort of spaghetti-like potentials in inflation models, things like resonant non-Gaussianity, primordial features, and these can imprint oscillatory features in the bispectrum as well as the power spectrum. And then an unbiased way of showing what's important, you can also consider the cosmological collider. So this has received significant attention from the theory community, as highlighted by the overwhelming number of citations that I put. And the idea here is that you have particles with mass of order the inflationary Hubble scale, and they can imprint characteristic bispectra on the large-scale structure of the universe. And so on top of this, of course, many people in this room have developed the pipelines and methodology we need to actually analyze the bispectrum with data. And so now we're looking at the bispectra in surveys, and we're getting better and better data. So let's try and see what we can get out of these measurements. And so our main motivation is this scenario, but it's worth keeping in mind the others. And so to go into a little more detail, the idea is here that you have some massive particle in the early universe, and as it interacts with the inflaton, you can improve characteristic limits in the squeeze limit of the bispectrum. So this squeeze limit refers to one mode, the so-called soft mode, being much shorter than the other two, and it looks roughly like the diagram here. But crucially, this is actually very protected by symmetries, the bispectrum you predict in this limit. It takes the following form, where the main thing is that the so-called power law here depends on the mass of the field. And so by probing this bispectrum, we can try and constrain the mass of these particles. So if you have a massless particle, you get local non-Gaussianity. But in this type of talk, we're going to look at masses greater than 3/2 the inflationary Hubble scale. This becomes a complex number. And then the bispectrum inherits characteristic oscillations whose frequency is a probe of the mass. And so essentially, we want to ask, how does this modify large-scale structure? And of course, there's been some very nice work already looking at this, largely from the perturbative regime and looking at galaxy bias. But sometimes it's fun to consider things non-perturbatively, so we can run n-body simulations. And so the main thing I want to talk about here is we just imprint this type of bispectrum in the initial conditions of a suite of n-body simulations. We pretty much ask what happens to it. And so in our particular talk, I'm going to be focusing on something that's a little simpler. So I'm getting rid of this q over k to the 3/2 scaling. But we essentially have local non-Gaussianity modulated by some oscillatory function. And then we have some modified code where we can then put this in the initial conditions, run a simulation, and look at it. And so the first thing to do is just run the simulation and ask what happens, right? And so what I'm showing here is the evolution of the squeezed bispectrum as a function of redshift, going left to right, and as a function of scale. And so what you can see is that this tree level prediction, which looks just like sort of a sign in the way we're doing things here, looks pretty nice. But as you get to low redshifts, the oscillations are severely damped. And it seems like we're washing out a lot of this information. And so when you see a plot like this, there's really two questions to ask. And this is the focus of my talk. One, can we model the damping? And two, can we undo the damping? And so in terms of question one, can we model the damping? We need to ask, well, what is a squeezed bispectrum? So when we think about squeezed bispectra, morally, we should be considering the long wavelength modulation of a small scale power spectrum. And so what I mean by this is that, well, the long wavelength is obvious. We have it right there in the formula. But then the remaining two modes are really just measuring the local power spectrum. So the approach of squeezed bispectrum estimation is essentially taking your field, dividing it into boxes, measuring the power spectrum in each subbox, and correlating with the long wavelength mode. And so this also tells you how you should think about this theoretically. So instead of just trying to fully perturbatively solve everything, in certain regimes, like the squeeze limit, we can just replace this with a power spectrum, and there's a natural expansion parameter, which is the long wavelength mode, and you do this type of expansion, and then you get something that looks like the following. So you can write your squeezed bispectrum as essentially some response function to the long wavelength potential of the matter field. And so this is not new. This has been done for a long time by many papers, so I don't want to act like we're doing anything new here, but it's important to see that this is something that we can use to try and do our modeling. But crucially, there's two details. One, what we've been focusing on with my collaborators is that this is substantially enhanced in certain models of non-Gaussianity, or if you have equivalence principle violation. And two, there are some tricks you can use to estimate this non-perturbatively, so we can actually look at squeezed bispectrum beyond the nonlinear regime. And I'll give a quick flavor for this. The first thing is that In our type of bispectrum model here, we can do the exact same argument and say, well, this bispectrum induces a primordial coupling between the long wavelength potential and the local power spectrum. So you can use your favorite trig identity, and then you can essentially rewrite this as saying that what's happening is the small scale power spectrum is essentially being rescaled by a momentum dependent function. So in traditional local FNL, we often think of this as like a rescaling of sigma 8, and that's because we don't have this oscillatory function. But here you have something else where you're essentially rescaling the small scale modes, and this tells you how to compute the response function. You essentially modify the power spectrum in the initial conditions, run a simple n-body simulation, and finite difference. Or this is a little bit technical, but to make it a little simpler, all we do is we take standard lambda CDM type models, modify the power spectrum by some oscillatory function. This is just like the sigma 8 thing you do in local non-Gaussianity. Run it to redshift 0, finite difference the output, and you get what looks on the right, this response function. So this is all the non-perturbative behavior in the bispectrum can be captured by just simulating power spectra. Crucially, you can see that they're damped at low redshifts, but something that's going to give a hint at reconstruction is this damping is very well described by the Zeldovich approximation. So all this damping, this washing out of the signatures, is actually well captured by our lowest order Lagrangian perturbation theory type calculations. So then one last thing to do is we can look back at our previous plot, compare tree level, and replace it with our separate universe predictions. This is not a fit to the data. This is just saying it's another way of calculating the bispectrum. It goes straight through. So this tells you, one, we can model the damping. Two, I won't go into the details of this, but if you can model the damping, then you can create an estimator for FNL, and you can fit FNL from your simulations. And what I'm showing here is our constraints on FNL as well as this phase parameter. And you can see that as we go to lower redshifts, we lose information about FNL. This is sad. We're not going to be able to constrain these models at low redshifts unless we do something more clever. And two, you can see there's limited info beyond quasi-linear scales. So if you trust our modeling, I can tell you I can fit up to k of 1 and it's unbiased, but who cares if the error bar is the same as a k of 0.5? So that motivates what I'm going to talk about in the last couple minutes, which is can we undo the damping? And so there's been substantial work in the community focused on undoing damping of oscillations, largely in the context of the power spectrum to reconstruct the BAO feature. It's pretty well understood that the bulk of this damping comes from long wavelength displacements that we actually know how to undo via this reconstruction procedure. So then you can ask, do these reconstruction algorithms also work on oscillations in the bispectrum in this squeezed limit? And so here I'm using this iterative reconstruction code from Marcel Schmidtful, but realistically you can also do this with standard reconstruction and should find relatively similar results. And so then all we do, here we have our damping that was annoying us. You reconstruct the bispectrum, and we're actually getting pretty substantial improvement up to roughly k of 0.5. So reconstruction restores the oscillations. But you can also show that we can actually model the post-reconstruction bispectrum in this framework by simply reconstructing our separate universe simulations. So I can run the same nonlinear reconstruction type procedure, and I just run it on the separate universe simulations. It goes right through the curve. And that gets me to my last slide, which is to say that if we can reconstruct the bispectrum and do the post-reconstruction modeling, we can in principle improve our constraints on FNL by a factor of 5. So what I'm showing here is the constraints from the pre-reconstruction bispectrum. Of course, this is all in fairy tale land of real space matter, and we have to be a little more complex for bias traces in redshift space. But we get substantial improvement from the post-reconstruction bispectrum. And when we see these big numbers, we need to know where are they coming from. One, obvious, we're boosting the signal. You can see by eye, we're more sensitive to FNL here. But true reconstruction undoes the notoriously horrendous non-Gaussian covariance of squeezed bispectrum configurations. So here you can see the pre and post reconstruction correlation matrices, and you can see that things have gotten better. So to conclude, if there's one thing to take away from my talk, it's that post reconstruction squeezed bispectra are potentially a useful probe of new physics. Oh, I agree, yes. 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 So in this work, we just were like, let's get the squeezed limit correct, because this is also the most sort of model independent one you can predict. But there's actually was a nice paper that came out, I guess, about a month ago where they really do the full template and they use some modal type decomposition to generate the initial conditions. And I'd be interested to compare their squeeze limits where they use the full templates to ours, where we're really just getting the squeeze limit correct. But you're entirely correct that, yeah, there's additional shade. Yes. Yes. Oh, so this is slightly different, but yes, so this is an important point. So yeah, these models do not generate features in the power spectrum, which is why we're focused on the bispectrum. So to generate the bispectrum, we actually do not put oscillations in the power spectrum. You can look at the power spectra of our simulations, and they're not oscillations. We do some type of transformation like this. But this slide was saying that if you want to model this bispectrum non-perturbatively, sorry, then you get these types of response functions. So you need to compute this mode coupling term. And we're saying that if you want to compute this response, we should view this as, in local FNL, you compute the derivative of the nonlinear power spectrum with respect to sigma 8. And so it's not that you're changing sigma 8 of your simulations with FNL, it's that you compute the response. And in this case, so this is just for our modeling. It's like, but not for the actual bispectrum.
Okay. Yeah, okay. Yeah, go ahead. So origin of these oscillations, right, is a different resonance. And even though you have oscillations in momentum space, this is really the oscillations in real time in inflation, right? So when particle physicists, when they look for resonances, they somehow don't look for oscillations in real time, they work in energy basis and then they look for a peak, right? Because Fourier transform and oscillation maps into a peak in energy basis. The question is, have you thought about, or anyone thought about doing some kind of Fourier transform so that instead of looking for oscillations, maybe we'll be looking for some peaks, and if this could potentially be helpful?
So I think in certain scenarios, this could be helpful. For example, if you had like a primordial feature type scenario where you have a linear oscillation in K, then we can measure like the 3-point function and look for a peak similar to the BAO feature. In this case, I'm not sure because we have this logarithmic oscillation in mu log Q over K. So if you Fourier transform this, I don't think there's some natural basis that I can think of where we're just going to get a sharp peak.
Well, I can tell you about the natural basis.
Yeah, but observationally, is it a friendly basis to work in? Because also these are, I don't know, I don't want to Fourier transform this and then have to do the full model of like the real space 3-point function. It's kind of nice to work.
Yeah, I mean, this logarithm, you need to Fourier transform roughly with respect to kind of conformal time. Right? Because the overall scale of the sky maps into conformal time during inflation. So you kind of need to, okay, not just naively Fourier transform, you need to Fourier transform with respect to like a scale part. And that will turn these oscillations really in a peak.
Okay, yeah, maybe we can talk about this more. But observation, I think this sounds challenging. Yes. If it's just cosine, you can do BAO. Or, yeah. Yeah, so it doesn't depend much on this. So we've also run this at FNL equals minus 300 and FNL equals 0. And the nice thing about this is, well, sort of nice and not so nice, is that we have this very large covariance coming from mode coupling from gravity. So if you actually compute the covariance matrix for like a fiducial value of FNL equals 300 versus FNL equals 0, they're almost identical because gravity likes generating squeezed bispectra more so than FNL. Yes, so in this case, we typically look at squeezing factors. I guess so the soft mode, I take up to around 0.04, 0.05. And then the hard modes, I'll go all the way up to like 1, but I'll start around like 0.2. And in this, I think, yeah, you need a squeezing factor of order 5 roughly to start getting unbiased constraints. So if we look at a non-squeeze configuration, our constraints are biased. This whole approach doesn't work at all. But the estimator itself is like a full bispectrum estimator. I'm not really doing this like dividing into boxes and measuring the power spectra. Oh, this was just a cartoon. But at the level, if it's very squeezed, the estimator is identical to actually doing this. You can write it out, and it's identical to a power spectrum estimator of the squared field with the long mode. But no, we just used a full standard bispectrum estimator.
Yeah, very quickly. Yeah, so going back to this undoing procedure. So
Yes.
I expect this result to be, if I think about again the bump that Victor was saying, I mean, the more this bump approaches like nonlinear scales, the more I should see that the undoing doesn't work. Because modeling
Yes.
nonlinear scales is too challenging. So do you see this? The results I'm seeing are at fixed frequency of your oscillation, and which frequency have you picked?
Yeah, so we chose, essentially kind of the shame of these collider models is that you increase the mass, you get higher frequencies, which is more fun to look at, but you also get some suppression factor, like this e to the minus m term. So we looked roughly at some of the largest frequencies that are being searched for observationally. So there are these paper by including Oliver and others in this room looking for the cosmological collider. So we did mu equals 4, which is one of the larger frequencies that they still searched for. I think when you have these logarithmic oscillations, it's kind of hard to define the scale in real space of where this peaks. I think if we had linear oscillations in the power spectrum, we could do this exercise of varying the frequency and asking like, how effective is the reconstruction procedure at getting the DAO-like feature as a function of frequency? But when you have this logarithmic thing, it's a little weird because you Fourier transform it and it goes over many scales. So.
Okay, let's thank Sam again. Oh yeah, you want to put your laptop. So okay, you're already connected. It does. Oh, you also have your own, okay. That way. So. Okay, so the next speaker is Will.